The first step in solving three-dimensional equilibrium problems, as we saw in case of two dimensions, is to draw a free body diagram. Before we can do this, however, it is first necessary to discuss the types of reactions that can occur in the three-dimensional support. As in the two-dimensional case, a force is developed by a support that restricts the translation of its attached member, and a couple moment is developed when rotation of the attached member is prevented. For example, the ball and socket joint prevents any translation of the connecting member. Therefore, a force must act on the member at the point of connection. This force has three components having unknown magnitudes Fx, Fy, and Fz. In single journal bearing, there are four unknowns. The reactions are two forces and two couple moment components, which act perpendicular to the shaft. In single journal bearing with square shaft, there are five unknowns. The reactions are two force and three couple moment components. In a single thrust bearing, there are three reaction forces and two couple moment components. A single hinge connection has three reaction forces and two couple moment components unknown. Please note that the single bearing support and single journal bearing with square shaft, the single pin, and the single hinge shown here resist both force and couple moments. If, however, these supports are used in conjunction with other bearings, pins, or hinges to hold a rigid body in equilibrium, and the supports are properly aligned when connected to the body, then the force reactions at these supports alone are adequate for supporting the body. In other words, the couple moments become redundant and are not shown on the free body diagram. For example, consider the two rods and plate with their associated free body diagrams. As stated earlier, when a body is in equilibrium, the net force in the net moment equals to zero, such is the summation of all force components and moment about O is zero. These two vector equations can be written as six scalar equations of equilibrium. These are shown here. The moment equations can be determined about any point. Usually choosing the point where the maximum number of unknown forces are present simplifies the solution. Forces occurring at the point where moments are taken do not appear in the moment equations since they pass through the point. Remember, when a body has more supports than necessary to hold it in equilibrium, it becomes statically indeterminate. A problem that is statically indeterminate has more unknowns than equation of equilibrium. Here we have six unknowns, but there is nothing restricting rotation about the AB axis. In some cases, there may be as many unknown reactions as there are equations of equilibrium. However, if the supports are not properly constrained, the body may become unstable for some loading cases. Let's consider this example. The rod supported by the thrust bearing at A and cable BC is subjected to an 80 pounds force. To find the reactions at the thrust bearing A and cable BC, we need to follow these steps in a sequence. First of all, establish a proper XYZ coordinate axis. Draw a free body diagram of the rod. Write the forces using scalar equations. Apply scalar equations of equilibrium to solve for the unknown forces. So once we establish the coordinate system, draw the free body diagram as shown here, and then apply scalar equation of equilibriums in appropriate order. So first we apply in the x direction, which yields Ax equal to 0. Then apply the moment equation of equilibrium, which gives BC equal to 40 pounds. And now apply the equation of equilibrium in z direction. It gave us Ez equal to 40 pounds. Now write scalar moment equation. Guess about what point? Well, about point A. Solving this equation, it gives moment about x-axis 240 pounds and moment about z is equal to 0. Thanks for watching.